I'll start the recording. So anyway, since I didn't say it while I was recording, for number one, when it's asking you to find the number of bits, you have to basically say, okay, how many rows of memory do I have? And in that first example, whatever. So in that example, we'd say, okay, well, we have 4 address bits, and we have 20 data bits. And so we have to ask ourselves, well, for the address, how many different rows can you encode with 4 bits of address? How many unique values can you encode? And the answer would be 16. Because just like if you're doing a truth table, if you have 4 inputs on your truth table, you're going to have 16 rows. It's always going to be 2 to the number of inputs n. So here, when n is 4, you get 16. So our memory, and you'll actually see this on page, the next page, that actually it actually visually shows the memory from address 0 to 15, like this. And it actually shows as well the data encoded at each of those places. And you can ask yourself, okay, well, I know how many rows of memory there are. So I know how much data I'm storing in terms of rows. But how much data am I storing at each individual spot? So in this first spot, and indeed at every spot, we're storing exactly 20 bits. Because we know that when we read from memory, we get a 20-bit output. And if we get a 20-bit output, that means each of these individual boxes is 20 bits. And so we say, okay, there's 20 bits here, 20 bits there, and 20 bits for all of the boxes. And so you say, okay, 16 rows times 20 bits per row. And I guess maybe I'll even write that out explicitly. And you get 320 bits. And so you would just write that as the answer. In general, the number of bits in memory is always going to be 2 to the n, the number of rows, times the data bit width. So I guess I'll say width. And just keep in mind that this 2 to the n is also sometimes called the depth of your memory. The depth is how many values you can store. So just in general, it's just the depth times the depth. That's the amount of memory you can store, and if you have those units in bits, then that's how many bits you can store. Okay, so now that I have that on video, did you have any other questions for me?
Oh, and then when we have, imagine we have like 100 bytes or something. Is that even possible to, like, when we're gonna? Is it total bytes essentially is just asking us to divide the total amount of bits, right, into by 8?
Yeah.
What would happen if we had like rounded numbers, or?
You're asking what would happen if what?
Like if we had decimal numbers, or like.
Oh, like it didn't go in nicely?
Yeah.
Well, I mean, think about it like this. If you have 4 bits, how many bytes do you got?
16. Oh, 4. How many bytes? 2?
Nope. If you have 4 bits, remember that a byte is 8. So you actually have only half of a byte. So you would just say half a byte. Physically, that's correct. And actually, in terms of memory, that's also correct. Because literally, what we mean when we say half a byte is we mean 4 bits. And 4 bits is something we can actually do. We can do in hardware. If instead you told me that you had half a bit, then I would be more skeptical, because that doesn't really make sense. Half a byte is fine, because we can break that down into a smaller unit, bits. But bits are the smallest that we can go. Can't really do half a bit. So there's nothing wrong with decimal values so long as it's not a decimal number of bits. That would be bad.
Nice. Okay, that makes sense.
And if you were to look at the storage right now in my laptop or in your laptop, and you looked, you would see maybe it says you have 4.2 gigabytes left. Well, that's reasonable to us. Literally means 4.2 billion bytes. And that's fine. That's a whole number. There's nothing wrong with that. Any other questions?
And then I guess to just finish it off for number 1.
Yep.
So when it says address signal is 12, so we just take a look at the 12, and then we just grab the data at like 0x the data, right? Yeah. Okay.
Yep.
That makes sense.
Yep, that's it. Now that I think about it, I'm gonna check to see what the tallies are. They haven't changed since I checked earlier. So I'm probably gonna end up holding my office hours on Friday at 2:30, because that's what it seems like most people want. So I think I'll make an announcement in the Discord at the end of the office hours to let everyone know. Okay, yeah. Any other questions?
So now we're going to go to RISC-V architecture and assembly.
Yep.
In that, when we're doing add I or like add immediate, we're expecting a constant, right? With a register.
Right. Yeah.
And so, but that register, if it's not 0 and we were to choose like S1 or whatever, would it use the value in that register?
Yeah, that's right. Yep.
Oh, okay. And then when it comes to load word or read word, or is it read word?
It's load word and store word.
Oh, store word, yes. It would not does it store the value of that register to our target register? Because first it gets offsetted by, right?
So you're asking for the difference between these two? Or what are you asking for?
Oh, okay. I suppose I'm asking on the 0 open parentheses S2 close parentheses, in that what happens first is that it gets offsetted by 0 or whatever value we put in, right? And then does it read the S2, the value of S2?
So basically, here's what happens. For both of these cases, it's the same. What happens is these two numbers together form your address. And when I say together, I mean you just add them. And so as you mentioned, yeah, you would read the value of S2. So say S2 currently holds hex 200. You would say, okay, this register holds the value 200. Hex 200 plus my offset of 0 is then equal to 200. And so hex 200 is going to be the address that I look up in my memory. So I go to that address and do whatever I want. I either write to the memory or read from the memory at that address.
Let's see.
The inside of the parentheses always has to be a register, and the outside of the parentheses always has to be an immediate value, though this could be non-zero. This could be, say, 5, though actually that's a bad number. I'm not going to use 5. I'll do 8. And inside of the parentheses you could have, heck, you could even have the 0 register if you wanted. That's fine too. Here, the effective address would be 8 plus the value, well, the 0 register holds the value 0, and so your effective address would be hex 8. And that's where you would go looking up in memory and say, okay, I'm going to go find address hex 8 in memory, and then I'm going to go run over to it and figure out what the data is stored at that location. And then from there, you're either going to take that data and move it into the register you have here. That's for load. You're loading from memory into this register. Or you're storing to memory, which is you take the value that's currently in T1, and then you would deposit that into your memory. You would write it to memory.
Okay, so, in this case, we would for store word we would deposit T1 into address 8, right? Or
I mean, I messed them up a little bit. So
oh, okay,
here would be address 200, but yeah.
200. Yeah. Okay. Okay. Thank you.
So the way you write it would be like. So for load word and for store word, another way you can write it looks like this. So for store word, you're changing the value at memory. So you can say the memory at address 0 plus whatever the value of S2 is receives the value stored in T1. So literally whatever is in T1 is going to be written to the memory at this address. And load word is just you swap the order of the two. T1 is going to receive the value of memory at, in this case, 8 plus the 0 register. So all you're doing is swapping the two. That's the main difference between the two. You're either writing to memory or reading from memory, or writing to the register or reading from the register. Okay. Any other questions?
I think you've answered like most of the questions I had when it came to assembly for now, I guess. Yeah.
Okay, cool. Oh, just so you know, it's called RISC-V. The V stands for like the Roman numeral 5.
Mm-hmm. Is that like the fifth of RISC
It's like the fifth
development, right?
iteration or
Yeah,
something
iteration.
like that of the architecture from Berkeley. Yeah. Or wherever. I think it's from Berkeley. I don't remember. I think that's where they made it. I'll go and erase this from the board.
Did you go over like the if statements in assembly?
Sure. Yeah. Have you guys gone over those in class yet?
Yes.
All right. So our goal is to convert something in an if statement to assembly, RISC-V. So it mostly depends on what's inside this if statement, but I'll just do an example. I'll say if this happens, so if x is equal to 1. And so whenever you have these conditionals, you have to use conditional instructions. So these are your branch instructions. So you have a few of them. Two of these are going to be pseudo instructions. E greater than equal to. I think this one's wrong. I might be writing that one incorrectly. I think it's a different three letter for this one. But you have branch if not equal, branch if equal, branch if less than or equal to, branch if greater than or equal to, branch if greater than. Two of these are pseudo instructions. You'll talk about pseudo instructions a little bit later, but you can still type them out in assembly and it'll still be able to understand. It just changes it into real instructions. So if you want, I can talk to you about why you have pseudo instructions and why you turn them into real instructions, like what that means, but we'll get into that in a bit. Basically, you're going to pick one of these depending on what's inside the conditional statement. And typically you actually pick one that is the exact opposite of this. So if in your conditional statement you have equals, you would probably want to pick branch if not equal. Because typically the way that the code goes is you have your whole body of the code up here, and then the rest of the body of the code down here, and then you have an if statement. And if the thing inside of the if statement is on, if it's true, then you execute the stuff within. If it's not true, then you skip. Then you skip all the stuff inside. And so that's what we're going to focus on, the negative aspect. If not equal to 1, then branch. Branch past all of that code. And so the way you would write this is something like this. So let's say, for example, that S3 currently holds the value X. Just for the moment, we'll say that X is stored currently in S3. The first thing we need to do is we need a number to compare to X. Specifically, we need to compare it to 1. So I'm going to have to store 1 into a temporary register, or just any register. So here's what I'll do. So what I did there is I added 2 numbers, a register with an immediate, and I stored it in T1. So after this line executes, T1, whoops, not 0. After this line executes, T1 holds the value 1, because 0 plus 1 is 1, and that gets stored into T1. Okay, are you cool with this stuff so far?
Yes.
Okay, so now that we have a value to compare against in a register, we can now use this instruction. So I can say branch if not equal. And so then I write the 2 things I'm comparing. So the 2 things I'm comparing are X and 1. And here they're S3 and T1 that I'm comparing. And the third thing that I write is the label that I want to jump to. So in code, like in C code, you have these curly braces to denote the internals of your if statement. And if you don't enter it, you go basically right past the last curly brace, and you start executing from right after that. The label works the same way. The label is going to be this end curly brace, basically. And so what we say is, I'm going to say, you can call this anything. It's any word, just like how you can name a variable, like in C code, anything. You can name a, what's it called? They're called targets. You can name a target whatever you want. I'll call it, as long as it's not a keyword, I don't think you can name it like an assembly instruction name. But other than that, it's fine. I'll call it skip, I guess. Because if we jump to that label, that means we skipped over the internals of the if statement. And so in your assembly code, you would then write something like this. Literally, this is what you would put in your text editor. All this stuff over to the right-hand side of these. You would type this label such that it matches that one, so that it knows when S3 and T1 are not equal, that you're going to jump to this spot in memory, in your program memory. So this is where you're going to jump in your program. And then you can start executing whatever the stuff was that was after the if statement. The stuff within the if statement is what goes in here. So again, going through it one more time, we say, okay, we have an if statement and we want to compare 2 things if X is equal to 1. Typically, to make it easier for yourself, you pick the opposite condition. So if you're saying X equal 1, the assembly instruction you select would probably be not equal. And so we're comparing X, which is in S3, to 1, which is in T1. And we're checking if they're not equal. In the high-level code, if X is not equal to 1, we're going to jump past the if statement, which is what this does. If S3 is not equal to T1, then we're going to branch to the skip label, which is down here. And that's skipping over all of this internal stuff that would have been inside the if statement. If they are equal, then this is not going to jump you to the target and is instead going to move to the next line. And so that's over here. If they are equal, you execute the internals of the if statement. If they are equal, then you execute the internals of this block. And so that's the typical way you do comparison. You do like if statements and comparisons and conditional checks. And you do the same thing for like while loops and for loops. The only difference is in a while loop, you have a line at the end, which basically just jumps you back to the top again. Okay, any questions on that?
When you say a while loop jumps you back to the top, like in high level code and assembly code, or
In both, yeah. So
in
in
both?
high level code, a loop literally means you do it over and over again. So you run through the code sequentially, and then you jump back up to the top, reevaluate whether or not you should keep looping, and then if you're supposed to, then keep looping. Otherwise, jump back and leave. And in
Okay.
assembly, it works the same way. You'll probably get into that in some of the last ones, but it'll be very similar where you'd just have another branch down here, and it's just, well, yeah, you wouldn't even have a branch. You would just have an unconditional jump. So if you got to this line, the last line before skip, you would then jump back up to here, and then execute this. And then if you needed to leave the loop, then it would skip you past it. And that's how you'd implement a loop. You'd just put an extra jump statement down here.
Okay, thank you.
Yep. I mentioned that two of these were pseudo instructions. I'm pretty sure this one and this one are the real instructions, and these two are implemented with other instructions. And I call them pseudo instructions. That's what they're like actually called. That's the formal name for them. And pseudo instructions are nice because you can actually type them into your assembly code, and the assembler will understand it and be able to do it. But the actual processor is not running this because that's not an instruction it can do. It's running whatever the decomposed instruction is that the assembler turned your pseudocode into. The main reason that we even have these is just because if we have if we have something like this, branch if less than or equal to 1, you can actually implement that using a different, using another instruction. Because remember what I said is you take a look at this and you say, okay, I want to compare it to the opposite. So just like we did for this one for x equal 1, the instruction we chose was not equal. So for this one, I'm going to choose the greater than or equal to. That would be this. And branch if greater than, or sorry, just greater than, pardon. The opposite of less than or equal to is greater than. And that would be this one right here. Branch if greater than. That's a pseudo instruction. And so we say, okay, well, we can't implement it. The way that it does it is it takes a look at one of the other real instructions, one of these two, and uses them to implement it. And so what it says is, okay, you're trying to check if this happens. You're trying to check if x is greater than 1. Because if it is greater than 1, then you're going to branch. And if it's not, then you're going to continue. So what it does is it says, okay, but this means the same thing as if you just swap the two around, swap the order, it means the same thing as this. X greater than 1 means the same thing as 1 is less than x. But if you look, less than is a real instruction we have. And so the reason why we have these pseudo instructions and why we can decompose them is because firstly, we have them so that we can easily write these things without having to switch stuff in our head. It makes it easier for us to type. But secondly, the reason why we wouldn't just implement all 4 is because that saves us on processor hardware. So we don't have to implement 4 different hardwares to do each of these. We just need 2 of them, and we can implement the other 2 in terms of the ones we already have. And that works for the other one as well. If we did it for the pseudo instruction for, let's do that one. So I'll do it this way. That would be less than. It'll be that one, and that'll be greater than. No, that's not the one. Okay, I'm trying to think of which one the other one is. So here we have greater than, which is implemented in terms of less than. So greater than implemented in terms of less than. And what I want to do is for the other one, these two are kind of paired up together. You can represent less than or equal to in terms of greater than or equal to. So if you have, say you want to check if say inside your if statement you have if x is, let's do less than or equal to 1, and you were trying to write code for it, you would say, okay, the first thing I do is I flip the condition, so I negate the condition, and that would get, I'll do actually less than. So you negate the condition and you get the following. So you want to check, you want to branch if x is greater than or equal to 1. Now here, x is greater than or equal to 1, that is one of my instructions, so that gets implemented directly. If instead I had, let's do it the other way. X is greater than 1, and I do the negation of that, then I have x is less than or equal to 1. Less than or equal to is a pseudo instruction, and so instead I have to write it in terms of branch if greater than or equal to. So I swap the order and I say, well, 1 greater than or equal to x, these two mean the same thing. And this is the actual assembly instruction that I write. In general, this works for a few different things, where you save out on instructions that you don't have to encode directly in your processor, but you can write a pseudocode. So, like, for example, I don't know if this is actually pseudocode, but I'll bring it up because it is kind of an interesting point. Sub immediate, subtract immediate is not a real instruction. It could possibly be a pseudo instruction. I don't remember if it is, but it's not a real instruction. And the reason why is because you can actually implement this with add immediate. Because let's say you wanted to subtract something. Let's say it was you want to take S2 and then subtract from it 8. So you wanted to do S2 minus 8 and store it in T1. Another way of writing that is you could just say add immediate T1 S2 negative 8, because we can specify negative numbers in our assembly code. And so actually, adding an immediate specifies the same thing as subtracting an immediate, because all you have to do is negate the sign. So if this was pseudocode, I think it is pseudocode, it's going to read this, and it's going to actually execute this. So you don't have to have two separate operations when you can actually just use one instruction to do both. Okay, so I know I went on a decent bit of a tangent there. Did you have any questions for me?
Oh, no, you were explaining it really good.
Okay.
I was just thinking about it like how we did it with our ALU, in which like we would have a signal and then we would just invert that to get like if it was less than we would be able to get greater than or equal to.
Yeah,
This
exactly.
is kind of like that same type of thing.
Yeah, yep, exactly.
Okay.
We're saving out on hardware. We don't have to make a subtractor for our ALU. We could just use the adder to do both, and we just have different inputs depending on what we're trying to do. Yep. Did you have any other questions for me?
Okay, just to recap, when we're using adders or subtractors in assembly, we're gonna store we have our destination register, and we're gonna store a register plus or minus the immediate, right?
Yeah.
And then that will hold the hexadecimal, right?
I mean, you could represent it in decimal, but it's not really hexadecimal or decimal. It's binary. But typically, we represent the numbers in hexadecimal.
Okay.
So like, so if I said add immediate, this is your destination register, and then you have, I think it's RS, and then the immediate. What this translates to in kind of like an equation form is the following. RD receives the value of RS plus your immediate. So what you said is correct. And if you were to type it in high-level code, you would type it like this. So this and that, this in assembly and that in high-level code mean the same thing. Similar for if you're not adding an immediate, because there is a just add instruction where you're not adding an immediate, just you're adding two registers. So you have the RD, and then you have two source registers. So you have your one destination and then two sources. So RS1, RS2. And here you'd say, well, RD is going to receive the value of RS1 plus RS2. And it's a very similar concept. You can rewrite a lot of the other assembly instructions in terms of high-level code, just to make it easier to understand. Though you can't do it for all of them. Some of them don't have, well, most of them have a nice high-level equivalence, but when you get into, like, you're not even going to get into these kinds of instructions, but when you get into privilege instructions, they don't have nice counterparts in high-level code. You have to actually write them in assembly with inline assembly, stuff like that. Anyways. A lot of the ones that you guys will be working with, you'll be able to write out like I did for those. And so it makes it easier to understand if it's written in terms of high-level code.
What are privilege assembly?
So there's a bunch of different types of instructions depending on what kinds of things that you're doing. So there's the basic, like, logic, arithmetic instructions for ANDing, ORing, adding, subtracting, doing computations. There's storage instructions, there's jumping instructions. And then there are special types of instructions that you don't really get into in class, like privilege ones. As an example, when you have a processor, like a real processor that you're running in your computer, you typically have three kind of levels of, I guess, hierarchy and importance in terms of what is in control of your system. So there is the user level, which is where your programs are typically run. And then there's the kernel level. Kernel stands for just like your operating system. And then above that is the machine level, so the actual registers and stuff. And so what can happen sometimes is you can execute an assembly instruction which results in an error, some sort of error. And like, maybe say divide by 0, something silly like that. And occasionally, for specific types of errors, what happens is, say you were running in the user level where you're just running some code. Occasionally, if you get an error, it's typically either called an exception or an interrupt, though I think for software it's mostly called an exception. So you get some software exception, and what happens is the program's like, or the computer says, okay, wait, I'm in user level, and I just got an exception. I'm going to elevate this to the next guy up and have him handle it. These levels of hierarchy are called the privilege levels. So the machine level has a higher privilege than the kernel level, the operating system, which has a higher level than the user. And so you go up in privilege levels to handle these kinds of exceptions where something bad has happened in the code. And the reason why is because if something goes wrong in your code, you don't always... Well, I guess I'll say it like this. There are some instructions that only particular privilege levels can execute. Because if you're trying to run code that's going to, just as an example, if you download software, malicious software, and it tries to, overwrite your entire operating system and replace it with something else. Typically, when trying to do that, it's going to call an instruction which it is not allowed to call, because there are specific instructions which you can only call at specific privilege levels. And so those are privileged instructions. And so that malicious code you downloaded, that's running at the user level, and then it tries to execute this one instruction to, I don't know, delete your OS or something silly. And it's like, okay, wait, you just called an instruction that requires a kernel level clearance or privilege, but you're at the user level. You can't execute that. So then it brings it up to the kernel level and it says, hey, this guy was trying to execute this instruction. What happens? And so those are the privilege levels and that kind of thing. You don't really get into that a whole lot at all until when do you get into that? So there's processor architecture, which is CPU 300. You don't get into there. You might talk about it in 404. I don't even remember talking about it in 404, which is advanced processor architecture. The only reason I know it is because of some research I did over the summer. But yeah, that's some stuff. You could also look up the privileged instruction set for RISC-V if you're curious on the details of that. But you're not going to talk about it too much.
Is that kind of like sudo in like Linux? Or is that type of different?
Yeah, I mean that's the same idea. I don't know if they actually are exactly the same. I think yes, or kind of, because I believe if you're just regularly running commands, that is at the user level, and if you type sudo, it's like running it at the, I believe it's like running it at the kernel level, and like as if you were the operating system. So it's very similar to sudo. If it's not similar in the sense of being exactly the same, it's similar in idea. So it's a good comparison.
Okay. Yeah, I've heard of like the user space and the kernel space, but I've never heard of the machine space.
Yeah, the machine space is above both because, right, the kernel space is running on the machine. So the machine gets final say. If the kernel's trying to do something stupid, then the machine's like, hey, buddy, hold on. Come on now. And you can't really get any deeper than the hardware level unless you want. Well, I mean, you can't really go any deeper than the hardware level. There's nothing below that has actual decision-making capabilities.
Doesn't users get like VRAM? Like,
Pardon?
don't users get virtual memory?
Yes, any program that is being run or anything gets memory allocated, virtual memory allocated for that particular program. It just depends on what the program is and how much memory it needs.
I see. And so how does it actually give more memory?
How do you get more memory?
Yeah, like with VRAM.
It depends. If you physically don't have memory, you can't. You have to replace old stuff. And so typically that's what's done. If like in RAM, if you have, I guess you'll talk about caches in CP 300, so I'll use that. A cache stores basically the memory that you're using really, really often, and it's super fast, but because it's fast, and to make it fast, typically cache is located super close to your processor, instead of being like in like a hard drive off the chip or off the motherboard, connected via some interface. Because it's closer, it's a lot faster in terms of access times. But because it's closer, there's not as much space you have to actually put memory. So typically, the closer you get to the processor, the smaller the cache size gets. And also the faster that it gets. And so what you say is, okay, on my processor, on the caches next to it, I have memory that I'm using all the time. And if I'm not using a particular thing of memory, then I'm probably going to overwrite it with some new thing that I'm using pretty often. And so just in general, there's a few different ways to design cache, like in terms of how or when or why to replace. One simple one is just if you're full, like if there's no more space left in your cache, go to the oldest thing, which hasn't been, the one that hasn't been used in a while, and replace it. That's one way to do it. And so in this way, you kind of get more memory. Again, though, that's replacing other stuff, and that's just for RAM. If you're talking about memory in terms of storage, like long-term storage, you can't physically get any more storage than whatever's on your hard drive. There's no way around it.
Okay, thank you.
Yep. Got any other questions for me?
Trying to process in what you just said.
No, you're good. No worries. Take your time. Just let me know if you have any questions.
Okay. You said there were interfaces that like connect that were working together, right? With like the hardware, like the
Yeah.
cache and the.
Yeah.
So would that be like the same as like an API or?
So when I say interface, well, I mean like a hardware interface. So a and then there's the protocol running on that. So like you have physical connectors, which is the interface, and then you have the protocol running on those what's it called? The protocol running on those connectors, which isn't it's at the hardware level, so it's not an API because it's all done in hardware. Rather, the information you're sending on the wires, that would be API.
I see.
The actual way that what I was referring to is basically if you plug in your NVMe into your motherboard on your computer. So the NVMe is like a little storage unit, and it holds memory it holds its storage just like a hard drive, and you can get them up to like 2 or 4 gigabytes or 2 or 4 terabytes of storage. So you plug it in, and it plugs into an NVMe socket, and it's an NVMe interface. So it's a very specific way that they design the actual like wires that come off of it. They're not called wires, traces. The way they design the traces, and then on those traces you run a protocol which basically sends information back and forth very quickly, and that's done in hardware. And then the information that's actually being sent, that's your software, or that's your API stuff.
Mm-hmm.
And pretty much like when you're assembling a computer, if you've ever built a computer or seen one built, pretty much everything runs off of some sort of protocol or interface, because you have your CPU socketed into your motherboard, and then everything that's connected to your motherboard has an interface for it. So your RAM has a DDR5 interface. Your storage has either a hard drive, or in this case NVMe has an NVMe interface. And your graphics card has a PCIe, Peripheral Interconnect something Express. I can't remember what the C stands for. But it has a PCIe interface, and it communicates via that. And then I'm trying to think of what the other big components are. That's most of them. But they all have different interfaces to communicate with that all latch onto your motherboard.
And in terms of hardware, the motherboard would just be like a PCB, right?
Yeah, it's basically a PCB. Yeah.
Okay.
Just a big, complicated PCB.
Yeah.
Any
I
other
have one more
questions?
question. Oh yeah. So drivers are just like when we say like we need to upgrade our drivers, what does that really mean?
That's a good question. So your driver is the software that runs your peripheral, whatever
Hardware.
it is.
Okay.
So you have hardware, and then you have software running on that, and that's your driver. And then you have that software interfacing with other software through an API. And your driver is, well, when you update your driver, it's just they typically do it to like get rid of bugs, or to, I guess, improve the software itself. But it's just the software that is telling the hardware how to run. That's basically what your driver is. It drives or directs the hardware. That's why it's called a driver.
I see.
And as I'm sure you've guessed, I'm skipping over lots of very minor nuance and details that are
Yeah.
lots of time to explain and stuff that I certainly don't know because I'm not a driver software engineer. But that's like the basic gist of it.
For clocks,
Mm-hmm.
where is the crystal located? By the CPU?
Like where, like on your board, you mean? Where's the crystal located?
Yeah. Mm-hmm.
Well, typically there's like this little package that contains the crystal oscillator, and you just solder that onto your board. In terms of what's inside of that, I actually don't know. That's a good question.
Oh. Because when you hear it and it's just like it's just rapidly like just shaking.
Yeah, it's not shaking. I think you just apply a voltage to the crystal, and the crystal resonates at its like internal frequency, and depending on the crystal, that's a different frequency that it has. That's the way that it's been explained to me. I don't know too much about crystal stuff though, besides just plug it in and it generates this waveform.
What type of engineer would that be? Like the crystal engineer?
I have no idea what it'd be called. It'd probably be like a materials engineer. Is my
Mm-hmm.
guess.
Mm-hmm.
A very specific type of materials engineer, or maybe even like a physicist or something.
When you say microarchitecture, the scope is like the CPU, right?
When I say microarchitecture, that's like how you make. So if I say architecture, I'm kind of referring to like the instructions that I can run on my processor. And if I say microarchitecture, typically that means how you made the architecture, how you actually implemented the instructions in hardware, or how you gave it the data path
Oh,
to implement the instructions. That's typically what
I see.
you refer to when you say microarchitecture.
Okay. And then system architecture is how they all combine.
It depends on the context you use it in. In the context I've heard systems architecture, that's like, yeah, like how you combine multiple systems and how they interface with each other. But I'm sure it's used differently in different contexts. Any other questions for me?
Not that I can think of. You've pretty much answered a lot of the questions I've had
Yeah, no worries.
for a long time. Thank you very much.
Yeah, I've had a lot of those. Like, I had a lot of those questions myself when I was just in general, just thinking about stuff and not knowing things. So, you're very welcome. I guess since you don't have any more questions immediately, I have a question. Um, what made you go for CPE? Because I think you're a CPE major, right?
Yes.
Yeah. Why'd you go
Um,
for it?
I was supposed to be civil, but civil engineering, but I didn't really understand. I still, to be honest, I still don't know what civil engineering does. And so I was, and when I heard the word computer and like computer engineering, I was like, oh, okay, maybe I'll start learning like how it works.
Right.
And I had no idea how computers worked at all. And so going to like my first CPE class, and then just seeing ones and zeros, I had no idea what it meant.
Yep.
Yeah.
From what I know, civil engineering is just like when you build static objects, things that don't move, so like buildings and bridges. That's civil. At least that's the way I understand it.
And then there would be dynamic objects.
Yeah, dynamics would be more like mechanical engineers, I believe.
Oh, okay. I wonder why they separated like computer engineering and computer science. I mean, it makes sense because like there's just so much topic if it was just one thing.
I mean, the in reality, a lot of this is very interrelated,
Hmm.
right? Because you have the base level of the universe physics, the physics of stuff, and then on top of the physics, you build analog devices. That's where EE comes in. And then you use those analog devices, specifically transistors, to make digital devices, which is where your CPE stuff comes in. And then your digital devices all come together to make systems, computer systems, which you run your software on, which is where computer science comes in. So it's just, they're all different layers of the abstraction hierarchy. They're all very, very much interrelated, and it just depends. What you do just depends on what level of abstraction you prefer to work at.
Yeah, some more time. I'll turn back the question to you. What made you go into computer engineering?
Using my own stuff against me. Um, so when I was in high school, about to go into college, I knew that I wanted to do engineering because I thought it'd be fun to build stuff, make stuff. I didn't know what kind. I had thought about it for a little while. I didn't really want to do civil, and for a while I was between like electrical, computer engineering, and mechanical, and I decided I was more interested in like the electrical side of things, and so I was between electrical and computer, and I decided just why not computer engineering. There wasn't a particular reason why I did that versus electrical. I just thought it would be cooler to get kind of a middle ground, because you have CS, which is like almost entirely software, or just software really, and theory, versus EE, which is almost entirely hardware stuff like analog devices, and then CPE is like a nice little middle ground, so I can get a good bit of both. And so my reasoning was just, if I do CPE, I'll learn whether or not I like software or hardware more, and then I can focus more on that later down in my career. And I found out that I like hardware stuff more, so I personally focus and like pay more attention to that kind of stuff. But software is pretty cool too.
I mean, with computer engineering, like you would be able to get like even to like software engineering jobs to electrical engineering jobs, right?
Yep, pretty much. Just depends on kind of the things that I study. So, like, for example, I'm doing a lot of embedded systems classes right now, and that's pretty heavy on the software side. It does involve hardware, but it's pretty heavy on like C code and C++ code, because you use that to program your embedded system, and that's pretty software related. You could be a CS student, graduate, and then work in embedded systems, but typically people who do embedded systems in school have a better shot at getting to that stuff. So I could totally do that. Another thing I am interested in, another one of the core groups that I'm doing right now, is digital design, because I really like digital design. I like designing stuff from just digital logic. It's pretty fun. And so you could do a whole plethora of things for that. You could design, you could do lots of things like you guys are doing right now in System Verilog, where you can design modules in HDL. You could also go even further, go more EE. So one of the classes right now I'm taking is digital integrated circuit design, digital IC design, which is I'm trying to think. Have you taken 221 lab yet?
No. Is there a requirement?
In 200 lab, did you guys use breadboards at all? No, right? You just did it in Tinkercad.
We use it for one, I believe.
Did you guys have the black like chips that had the prongs sticking out?
The circuits, right?
Yeah, they're called the black packages. They're like made out of plastic and they have metal wire sticking out.
Mm-hmm.
So those are integrated circuits, and basically inside of that black package is just a wafer of silicon that's been cut up from the factory or the fabricator. And on that board, or on that wafer of silicon, there's actual logic. There's stuff on there made out of metals and made out of polysilicon and made out of doping concentrates and a whole bunch of a lot of stuff that would be a lot to get into. But basically, we're learning in this class how to make an integrated circuit like those ones that you guys are using in lab. So we're learning the software Cadence to make them, and also just in general how to make circuits like that. And so I find that stuff really, really interesting. I find it very, very interesting. So that's kind of what I'm thinking I would like to do ideally as a career, something like that. But we'll see where my life takes me.
Did you have to take a little like chemistry for that?
Actually, no. Now, when I did it, chemistry was a requirement, but actually no. At the moment, you don't need to. The only requirement for that class, it's with Dr. Baker. I don't know if you are familiar with Dr. Baker, but he's the one who teaches 421. I very much recommend taking that class if you're at all interested in learning how actual silicon is made into like parts that can process information. It's very interesting stuff. But you don't have to take chemistry. You have to take for that class, you have to take EE 320, which is the third circuits class you have to take. It's electronics. And then you have to take CP 100, which you already have, obviously.
Mm-hmm. And that's EE 421?
Yeah, 421. Yep.
Okay.
Yeah, if you wanted to, you could actually just look at Baker's website and look at his videos and his lecture material and see if it's interesting, because he uploads all of his lectures online, and you can just watch them and go through the homeworks and stuff if you're at all interested.
Yeah, for sure.
Let me type it in the chat. CMOS EDU. That's the name of the website that's Dr. Baker's website where he uploads all the stuff. So if you're curious, you can check it out and look at some of his other courses, because he offers some other stuff like power electronics and memory circuit design and higher level things like that. Lots of interesting stuff. I'm very interested in it.
Mm-hmm. Yeah, that's really cool. It's like you get it from the ground up.
Yeah, that's the fun part, building it from the ground up. Yeah.
Mm-hmm.
I don't think I could do physics though. That's too low for me. I can't go any lower than EE. Too much physics.
Mm-hmm.
Okay, it's about 6:30. So did you have any other questions before we end office hours?
Just one really quick one. Is there quantum computing in ULV or no?
Not that I know of. I don't think there's a course offered on that. Maybe occasionally graduate level courses are offered occasionally, like on a occasional basis, and they're all labeled like 795 as special topics. So for example, this semester I'm taking one of those classes, 795. It's high-speed PCB design. They might, one of the future semesters, offer something like that, but at the moment I don't think it's like a consistent class, and I haven't seen it offered previously, at least not to my knowledge.
Okay, thank you.
Yep. All right, I'm gonna go ahead and end the office hours right now. Thank you very much for coming in, and I will be back here same spot tomorrow at 5:30. So thank you for coming in.
Thank you very much for answering all of my questions.
You're very welcome.
Have a great night.
You too.